Hello. Hi. Welcome to this talk. This is I am Josh Suereth. I'm a senior software developer at Typesafe. I'm a big nerd. I'm an author. I wrote a book called Scala In Depth. If any of you have read it, this presentation is essentially let's find a nice word, but chewed up and like spit out from that book. So it's a lot of concepts from that book that help you, guide you into Scala. Scala In Depth is meant for people who are coming into Scala. This presentation is designed for people who are not comfortable with Scala. So before I start, hopefully I can see you all. How many of you code in Scala today? How many of you code in Scala professionally today? Awesome. How many have never seen Scala or touched it or know anything about it? Awesome. Even better. Even better. Okay, so this presentation will hopefully bring you into the zen of Scala development and exactly what it's supposed to be. So, yeah, a little bit more about me. So I wrote a book. I maintain the Scala standard library. I'm currently the release manager for Scala 2.10. Yeah, I did a bunch of other stuff. Yay. Okay, so let's start off. One thing I'm going to warn you about before I get into this slide, we're going to jump around a lot of different spots within Scala. This is kind of, an effective thing. So we're going to hit the basics, we're going to hit collections, we're going to hit some functional aspects. Okay, so try to bear with me and raise your hand if I'm losing you. Okay, so we can stop and slow down and cover a particular topic. Okay, all right, so in Scala, the most important thing, in my opinion, to learn first is to use expressions, not statements, okay? Use an expression. Here's an example of writing Java in Scala, okay? I define an error message. Can you guys see my mouse? Great. I define an error message, okay, that picks what error message to return. I declare a result variable. I look at the error code, and I return the correct string, or assign it to the result and return the result. Okay, I'm telling the computer what to do. That is a statement. Okay, create the variable, assign, return. Don't do that in Scala. Use an expression. Okay, now notice I don't even have a semicolon here because this whole function is one expression. On the right-hand side of a function is an expression. You can use semicolons to make a series of statements as an expression, but it's better to just have an expression. These things are really easy to maintain if they're only one expression. Okay, so we have error code. We match on it. Given each case, we just state the string. We express it. Okay? By default, the return value of this expression is whichever the last string, that was there, is the return value. So if error code is 1, I return network failure. Okay? Everything in Scala returns a value. Every expression. If statements return whichever portion of the if statement, whichever expression the if decided, it returns the last expression on that side. Match statements obviously return the expressions on the right-hand side of the case statements, et cetera, et cetera, et cetera. Okay, everything returns something. Even while loops return something in Scala. They return a very non-useful value called unit. So yeah, we return the first thing evaluated. So this is about not telling the computer how to fish. Okay, here's another Java-ish thing. I want to find people that live in a city, and I have a sequence of people. So I first define a set to store who I found. Then I iterate over the people and over the addresses of each people. If that address, the city is in that city, I put the person into the set, and then I return the set. Okay? I am doing a lot of manual work here. I am telling it exactly how to do things. If I am suboptimal here in this algorithm, and I have another piece of code that looks exactly like it somewhere else, and I fix one to be more optimal, the other one is still suboptimal. Okay? Because I'm telling it how to do things. I'm not expressing what I want. In Scala, we can use a for expression. Okay? So the first thing I do is I call people.toSet, because if I start with a set, I will return a set in a for expression. That's important. Whatever you start with is the collection you get back. But I essentially define something kind of like an SQL query. Give me the person, from the people set and the address set within people, okay, where the person's address is equal to the address set, if you will, and the address's city is equal to the city that I want to look up. Okay, I've declared what I want, and the implementation in the collections library should be optimal, right? That's the trust here. But I declare what I want, and I get back the same result. So I am stating what I want. I'm not telling it exactly how to do things. That is core to Scala, is this idea of expressions. Okay? Another thing that's core to Scala development is to use the REPL. We're going to shell out here. That is almost readable. Can you guys? What? Yeah, I believe I can. How's that? Perfect. Okay. All right. So inside of the REPL, I can instantiate values, and I can add things, see results. The important thing here with the REPL is when I do something, I can see the type. That's this colon string. It tells me what type the variable was. And I can see what its toString method is. I find that in Scala, more so than Java, you actually implement toString almost always because it's way easier to play with things in the REPL. But let's say I don't know how to use certain Java libraries. I can start looking for them. So let's import java.util, I don't know, random. That sounds good. And let's make a new random. I don't know anything about random. And I want to figure out what I can do. There's a, next bytes, next ints, next float. I'm going to do next boolean, and I'm going to use this to start my role-playing session. And I'm going to roll a bunch of die and see if I hit. Yay! Okay, I can role-play. Anyway, point being, the REPL is a great way to look at a library and start finding methods you didn't know exist, actually run them, see what happens, and develop what you feel is a good API. Okay? Then you write your tests. Then you write the code. All right? It's I call this experiment-driven development. Okay? When you're starting with a new library, it's really good to just get a feel for what it does, because sometimes the documentation doesn't cover certain behaviors, and you can really get a feel for that. Yeah, not you. There we go. Another thing that's important, and this is the same as from Josh Block's Effective Java, is you should stay immutable as much as possible. We try to make it way easier in Scala to stay immutable. So here's an example of why immutable code is good. If I have a person that has a var of addresses, okay, and I'm taking in an array of addresses, arrays are mutable. If I want to be safe, if I want to make sure that the addresses I take in don't get modified externally, I have to clone them. That's the only safe thing to do. Now I can trust other people that when they give me the array, they're not going to clone, but the only way that I can actually prevent bugs is to actually clone it, because it could change from underneath me. Okay? The same with when I give the address to other people, because it's mutable, I don't want them changing my internal state. I want to keep that my own. I have to clone it. So while mutable collections, you're talking about performance with mutable and immutable, if you have to code safe code like this for threads, where a lot of people can be touching things and you're giving access, this becomes drastically slower. Drastically slower if you try to code safely. Okay? Yeah, so we're essentially trying to prevent people from modifying our internal state. We are the only ones that need to control it. So we can make it an immutable collection. Okay? I can have a vector. Vector is Scala's, it's an immutable, essentially an array. It has really, really good performance characteristics. If I take in a vector, I can just assign it. I don't have to defensively copy it because it won't change underneath me. It's immutable. Guaranteed. So, even simpler, we have these things called case classes. Now I make the whole person be immutable, so that I don't have to defensively copy people if I give them somewhere else, because they can't change underneath me. Okay? The person is immutable, and the way you define an immutable class in Scala is you add this case in front of it. What case does is it makes this automatically a member of the class. So addresses is now a member that I can access. It's a value. I can give it a default, so I can instantiate people without defining addresses, and I just get an empty set. And I have a copy method, so if I do need a new person, I can use a var later where I can mutate, but what I do is I mutate the reference, and I just copy this person with a new address. Okay, so Scala makes using immutable values a lot simpler with copy methods and case classes. Everything is known at construction time of the person. I can add all of my validation for the class in the constructor because I know everything at that point in time. And changing is still simple. Okay, other benefits. Case classes give you a simple equality and hash code. Okay, we use murmur hash, so it's a pretty efficient hash code. There's no need to lock when you have immutability. If I'm passing something to another thread, I don't have to defensively copy it. And I don't have to lock it inside of my object in case I have multiple people looking at me. Once I expose that, it's immutable and it's safe, okay, once it's exposed. If I use case classes, that's where I get the automatic equality and hash code, or has code as I wrote here. But in general, I can write very simple equality and hash code methods if I don't use case classes, but I keep things immutable. Another thing that's nice is default or local mutability is still fine, right? If I use an immutable interface here, seek in this case is an interface that cannot mutate the underlying value, okay? If I define a new array buffer and I fill it locally and then I give it up, okay? The key here is there's an immutable interface, I locally create it, and I give it away. Because people can only see it immutably now, it's okay, right? I can get that internal performance on one single thread, I can expose it, and now it's okay for people to see it. This is actually an optimization technique that usually happens with FP, where you want to keep things completely immutable. You tend to take pieces that you can write inside of a single thread, mutate, and then expose immutability. That's fine, right? This is okay. We can still gain a lot of the benefits. All right. Another basic inside of Scala is to use the option class, okay? What should you use option for? I don't know if you guys saw JDK's 8 and the optional that's coming in. We have it in Scala, and so we can kind of show you best practices with that now. Anyway, so in Java, there is a what I call the null Pokemon game, okay? So here's an authenticate session method. I take in a session, a username, and a password, but all of them could have been null. Maybe some of them are null. So the first thing I do in the method is I check for null on everything, because it may or may not exist. And then if it exists, I do something useful. Otherwise, I return some default. Okay? You got to catch them all. What if I miss? You know, null pointer exceptions are really annoying. Worst part of coding in Java. So what we do is we create a wall. I call it the option wall. When we take in a username, we delimit that it may or may not be there. Okay? We may or may not have one. We're not sure. This method should work regardless. Okay? So what we do then is we use a for expression with options. Okay? It's as if we're looping over a data structure that has 0 or 1 elements. So I take the username if it exists. If it doesn't exist, this immediately returns a none option. Okay? If the password exists, I take the password. Otherwise, I immediately return none. If the length of the password is greater than 0, I have my validation. I will return none because I can't do anything if I don't have a password. And if I can authenticate, then I return privileges for that user. And then I have an option of privileges is what's returned. Okay? So the yield is where I actually do work, and I have all my checks that I have to perform. I cannot get access to the underlying data without calling some sort of method or using the for expression. Okay, you have to be aware that this thing may or may not be there, and the type system will prevent you from just using it. So once I get this option of privileges, I can use the nice get or else method to provide a default. You know, if I couldn't pull the privileges using the username and password because one or both of them weren't there or weren't valid, then I can just grab the session. Okay, this is This has a name to it, but I call it a wall. You're defining a wall, and the option is preventing this code in the yield from running unless everything was there. Okay? So yeah, the type system prevents misuse, and there's a lot of convenience methods like get or else. There's another method that's handy called or else, where if you have two options, you can have option or else option, and then get or else, and then the default. There's all sorts of ways to combine these things. They're rather nice. Okay, first of all, I've been using this for expression syntax here. How many people are unfamiliar with it? All right, we're going to cover it just real quick. So, what this is it's kind of like a for loop. For u in username, okay, p in password, and then these are filters, so like a where clause in SQL. And yield is the thing that gets returned finally. One thing about for expressions is username happens to be an option. So if I start with an option, I'm going to yield an option. If I start with a sequence, I'm going to yield a sequence. They can work on any data type that supports this kind of iteration. Oh, yes. Sorry, oh man, that's terrible. Yeah, this should be U and P, and this should also be U and P. This would fail to compile if you actually ran it. So, sorry. Okay. All right, another bit about Scala is style. Okay? Everyone argues about style. The important thing to remember about Scala is that we're Scala. We're not Java. We're not Haskell. We're not Ruby. We're definitely not Intercal. So if you're going to code in Scala, you should code in a Scala style. There are things that were good ideas in Java that are not good ideas in Scala. The same way there were things that were good ideas in C++ that are not good ideas in Java, right? It's the same kind of thing. So you can bring some of your style to Scala, and that's okay when you first begin, but remember that there's some behaviors you might need to unlearn when it comes to style and formatting, just because it's a different language. Okay, next, when it comes to object orientation, you should use def for abstract members. One thing that Scala has that's different than Java is you can define abstract values and abstract variables. Okay? So for those not familiar with Scala, def is how you define a method. Val is how you define a final reference to a member. And var is how you define a mutable reference to a variable. Okay? So here's an example. I define my really awesome sweet abstraction trait. Okay? It has an abstract height and an abstract width. And given those, I can calculate area by taking height times width. Okay? I define my class called square. I extend my really awesome sweet abstraction. And I override those vals with h and w. Should work, right? No. Because of the way construction happens, base classes are constructed first, and then subclasses. So when this value is instantiated, these things aren't defined yet. So what's the default value for an int on the JVM? 0. So yeah, I end up with 0 as my area, always, when I extend this thing. So that's because I allocate the memory for the object, I allocate my base class where I calculate area, and then I calculate square. Well, what I want is I want to allocate the object. I want to magically do something first. I want to instantiate all the abstract vals first. Then I want to instantiate the base class and then the rest of the classes. Okay, so how do I do this? Early initializers, this block right here. I extend an anonymous class that has the initializers, and then I have my really sweet, awesome abstraction. So that happens first. Does that sound complicated to anyone? Yes, it is. This is a very advanced technique if you're doing crazy things with OL. Don't do it. Use members. Use defs. Okay? If I define the height, width, and area, okay, I have two options when I define area. I can use a def, or I can actually use a lazy val. A lazy val is something that will be computed the first time it's accessed, and it will go read the state at that point in time. So I can defer the initialization of area to the first time it's used. Or I can just use a method. But specifically, height and width should be methods, so it's very apparent that I can't instantiate a val off of them. Here I can override height and width to be values, and when I call area, everything succeeds. Well, I can actually make this a little bit better. We can we can do the same thing, but I can actually define square as a case class. One nice thing about case classes is if I have abstract methods, I can override them with the members that are automatically created. So I don't even have to specify height and width again, but I can have an abstract trait that has it. Now construction still works fine and everything is great. And then, if you want to make area be lazy val or whatever, that's fine. But one thing that's fun about Scala is you can define a case class, extend a trait, and it overrides the abstract members. Okay. Next up, object orientation. We want to annotate our API or non-trivial return types. There's a question. Should we wait? We can wait. Okay, yeah, how about at the end? So, annotate API or non-trivial return types. This is where, in Scala, we infer return types. So if you noticed, I wasn't typing a lot of return values, and Scala will figure out what it is and write it in for you. The problem with this is, when I have a method like, say, person, okay, with name. What is name? Well, in this case, it's an option of string. Okay, but imagine if I were writing the name method, and I write name equals, open bracket, So it's a big, big, long method, and then at the end, I call hash code. What is it? When I first look at it, I kind of feel like it's going to be a string, but it turns out it's an int. Okay? But I have to read the entire method to see what the return value is, and I have to do type inference in my head. If it's a public API method or it's some sort of complicated return value, it's a good idea to annotate it. Okay? If you have a simple private, private methods that are nice and short, usually you don't have to annotate return values and everything's fine. But especially when it's a public API that people are going to go read, they want to see the name, they want to grep for it, and they want to see the input types and the output types. It's a form of documentation. Okay? All right, next up is that in Scala, object orientation, we have composition and inheritance. Okay? You should always prefer composition over inheritance, right? Well, in Scala, we can do both. So I can define a trait logger that has log, info, debug, that sort of thing. And I define a trait called hasLogger. HasLogger just tells me that I contain a logger. That's it. When I define my service, I extend hasLogger. And I can call a bunch of log methods. I can later on define a trait called hasAwesomeLogger that has a very specific logger. And when I construct my application at the end of the world or whatever, I would say new service with hasAwesomeLogger or new service with SLF4J logger. And it will pick which one to insert. So I can use inheritance to drive composition. And these traits essentially tag the composition. There's something in Scala called the cake pattern. And this is sort of a very simple entrance into the cake pattern. Okay. Next up, we're going to talk about implicits. How many of you know what implicits are in Scala? How many of you are scared by implicits? Okay, cool. All right, hopefully this helps. So what are implicits? We're going to talk about that. I can define a method called determinate, where its first parameter list takes in a matrix, and the second one takes in an executor context, the executor, that I'm going to run the determinate computation on, because I'm going to do this multi-threaded. Okay? I have a multiply method for matrices that I want to run multi-threaded, and I take another parameter list for the executor. Notice the implicit in front of it. It means that if the compiler can find me an executor on the implicit scope, it will insert it for me. By default, what I have to do with my code is define a pool, call determinate, pass in the matrix in the pool. Define multiply, pass in some matrices in a pool. Every single method on this API, I'm going to have to pass in the executor to run in, because I want to let you decide where to run each computation. And if you need to pass computations from one thread pool to another to segregate parts of your app, I want that to be configurable. But in general, people don't care. They're just going to make one thread pool and run everything. But I want the flexibility. So implicits come to the rescue. Instead of having all that boilerplate, I define the pool up at the top of the scope, Okay? And for that entire scope, that implicit pool is available, and I can call determinate without the pool parameter, and the compiler will figure out to insert it for me. So the way this works is when the compiler sees a method call that has an implicit parameter list, if you don't provide the implicit parameter list, it's going to go look and see if it can do it for you safely. Safely means that it can find one and only one value that can fit here. If it finds one and only one value, it'll put it there. Otherwise, it'll give you a warning saying, or an error saying, I couldn't find the value to place here. If I provide two executor pools in the same context, I cannot use implicits. Okay, it's gonna blow up. The thing, so basically with implicits, we are removing boilerplate within a context, and it has to be ambiguous or unambiguous. So the key here is that we need to limit that scope. We need to limit where these things are available so that we have the most flexibility when we write things, and we have the least amount of danger of things being pulled in that we don't want to be pulled in. With that said, here is how implicit scope works. The first thing we look at is lexical scope. Okay, so these are, when I type in a method name or I type in a value name, these are things that I can type without saying like foo.bar. If I can just say bar, that value is available in implicit scope. Okay, that's just the rules of lexical scope. Implicits in the current scope are things you've imported. So Scala imports and static imports are the same thing. You don't have to have a static import, which is why I say things you've imported. Part two are companion types of objects. This is an interesting one, and we'll get into it in a little bit more. But essentially, I can define a companion object for a type, and I can put a default implicit in there that gets looked up, if there isn't one in it lexical scope. Okay, so I have a hierarchy of I can put an implicit here, and that gets used by default, but the user can override it. Okay. One key of using Scala, once you get into implicit land, once you start using them, is to understand these rules, because you need to know where things are coming from, and you may need to make it clear. So you want to put things where people expect implicits to be. I tend to avoid imports as much as possible, because that is usually non-intuitive that this import had that implicit, unless you import explicitly something named implicit. Okay, it's just a general rule of thumb that can help. All right, so implicit values. If I have a logger and I have a companion object logger, I can define an implicit object that's a default logger. So everywhere I look up an implicit logger, it's going to check the companion object after it looks in lexical scope. Okay? After. Yeah, so that's the bit about implicit views, limiting which ones are in scope, making use of companion objects. Okay, we want to avoid implicit views. Anyone not know what an implicit view is? Okay, good, don't learn it. All right, these are bad. All right, I'm not going to go into detail about them, but they're one of the most misused features in Scala. Okay, an implicit view essentially allows you to convert from one type to another implicitly. So if I pass a string and I expect an integer, I can put an implicit that will allow that conversion to happen. And you lose object identity when you do that, and you have lots of possibilities of lots of issues. So they're not the best thing in the world. Now we have a new thing in Scala 2.10 called implicit classes, which are far better. It's the way that you encode extension methods. But anyway, that's a different talk. So another thing about implicits, we use type traits now. What is a type trait? I define a trait against some type T. What this is an interface for another class, for a T. All right? That's a type parameter in Scala. I can encode that type parameter into an array, and I can decode it from a byte buffer into that T. All right? So it's an external trait. It's not in the hierarchy of T. Then what I do is I define methods that say I can encode any generic T as long as there's an implicit encodable trait available for that T. Okay? I take in the T, I look up the encodable trait on the implicit scope, and I call encode on it. That's what this is doing. So this is my API, encode and decode. If there's an encodable trait available in implicit scope, I can encode and decode that T. Then inside of the companion object, I provide my defaults for things that I don't control. If I'm writing against somebody else's library and I need to encode, say, their JSON into bytes because I need a more efficient format, I can take JSON that I just read from REST, encode it into bytes, and send it somewhere else, or something crazy. That sort of thing. So in this case, I'm dealing with ints and longs. Implicit object in encodable extends encodable. It's now available on implicit scope anytime I look up an encodable. I can find an encodable of int. And I can encode it and I can decode it. So here's how we use it. I define an int called x and I call encode of x. And I get back an array where I encode it. And if I call encode with long, I get an error. Could not find implicit value for evidence parameter of encodable long. That message is configurable, by the way. I can use an annotation so that if the implicit for encodable isn't found, it gives you a different error message saying, you have not provided an encodable interface for long, please write one, see this documentation, blah, 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 blah. That's actually what we do in practice. Okay, so I can override the type trait locally. I can define an implicit object called int overridable encodable, where I change how ints encode, so they always encode as 1, and I ignore them, essentially. So now when I call encode of 5, I get array of 1, because I've used that implicit scope trick to put 1 in higher precedence. Inside of Google, when we had the Scala MapReduce library, this is how we did all of our serialization of data in and out of MapReduce, and it actually worked out really awesome. Because, I don't know if you guys use protocol buffers to send things back and forth in Java, but if you have protocol buffers with extensions, you have to do this crazy setup ahead of time, and it's different based on which message had an extension. Well, we used this little override. Whenever we were sending data that had an extension, we had to provide an implicit override in scope and then make use of it. Or we could import it from some library, and that really cleaned up everything. So it was very, very nice. All right, the benefits to type classes is essentially we can take an external class hierarchy that we don't control, and we can add methods to it. We can add behavior and write it against it. And we can even make it feel native. We can override things at the call site. We can separate our abstractions so that the same type can have 2 different implementations. If the implementation I have works really well on a particular computer, I can use it here for this context when I'm sending it over to that computer. And if I'm sending it to a different kind of computer, I can change the encoding. Again, you have to make sure you use the same decoding on the other end. But you can change the implementation of these things. And finally, I can use them to separate arguments into roles. So an example is if I want to copy from a source to a sink, I can use a type trait to define the role. The type F is the source, the type T is a sink. Why is this important? Well, if I wrote this method against, say, Java IO file, a file you can read to and write from. I can actually, write mistakes in the syntax of Java or Scala where I accidentally am writing to the source instead of the sink. But if my type trait only allows pulling from a source and writing to a sink, I can't screw up the order of these elements when I call the method. Right? So it lets you define roles. All right, next up, know your collections. So we have a hierarchy in Scala of our collections. The base is traversable. Traversable is anything that I can iterate over. Or not iterate, but anything that I can pass a function to that will run over everything in the collection. I can't necessarily stop it. Okay? That's actually a really useful collection because, say, I want to read from a file, and I want to make sure I open the file before I read, and I close it when I'm done. Traversable knows when you're done. So I can make a traversable against a file that just reads all the bytes, that sort of thing. Iterable is whether or not I can grab an external iterator. Traversable is the internal iterator. And then sequence is whether or not things, when I put them in the collection, remain in the same order. Set are things that are unique. Map, key value pairs. Here's the important one, index sequence and linear sequence. This is kind of new for Java people coming into Scala. Index sequence means I have an efficient indexing operation. So like an array or an array list, I can index into it efficiently. Linear sequence means I can do head-tail decomposition quickly, which is good for tail recursive methods. Okay? So in Scala, list is a linear sequence. List is not an index sequence. Okay? If you're coming from Java and you want to write lists like you would write array list for lots of things, you should use vector instead. Okay? Because vector actually has efficient index performance. List does not. List only decomposes head and tail. Another thing you should try to get comfortable with in Scala, this is the greatest playground in the world for collections methods. Anytime you want to do something in Scala, there's probably already an existing collection method that's there for you. In any application I've ever written, the most used library has been the collections library. Okay? By the way, this isn't for you to read all the different methods. This is just to show you how many there are. Anyway, yeah, so in any application I've written, the collections are the most significant library I've ever used. And the primary reason to use Scala at this point is really the collections library. It will drastically improve your daily lives. It's amazing. Okay, so when I want to integrate with Java, what's the best way to do that? Well, you should write your interfaces in Java to make sure you don't accidentally expose an advanced Scala syntax that looks ugly in Java, and then people won't hate you. Okay? Especially when you're working with the Java team. You want to make sure those interfaces are in Java. You want to make sure that you prefer primitives instead of boxed values. Now, why is that? Because in Scala, we don't have the notion of a primitive versus a boxed value. We just have int. We don't have Java lang integer and int. We have just int. The compiler figures out when to box and unbox for you. If you get a java.lang.integer, you actually have to convert it to an int. Okay? So if you have your API be primitive, then it looks better in Scala. It looks better in Java. You can keep people from hating each other for using things that don't work well in the other language. Okay. And here's an example. If I define my interface main in Java with lowercase int, and I use an array of string, in Scala it translates directly. We have an array of string and int. If I instead used a Java collection of string, then I have to do some massaging on the Scala end. If on the Scala end I want to use a Scala collection, I have to do massaging on the Java end. So it's best to provide that API in Java and then have your Scala code in a fun Scala world, and then all the Java developers can see things the way they expect. Okay? All right. Finally, learn patterns from functional programming. All right? Let's talk a little bit about asynchronous programming, because that's a hot topic, and that's where Scala can really excel. All right? I have an asynchronous API, get person. I give it an ID, I get back in the future some person. Friends of, I give it a person, I get back in the future a sequence of people or person. Interests of, I give it a person, I get back a sequence of interests. Let's imagine that the social graph, where I get friends, and the actual data, where I get interests, are two different servers, okay, two different things that I'm hitting. So I want to make those asynchronous APIs separately. The same with person. We'll just pretend, okay, this is, I don't know if you would do this in practice, but we're going to pretend. What I need is I need to make a front page context where I have a person, all of his friends, and their interests, and his interests, to display my front page. Okay? So I need to make all of these asynchronous calls, and I want to do that so that the whole thing is asynchronous. I don't want to block the thread that the request came in on, waiting for all this data, because I'm still losing. Right? I can still only handle the number of requests that I have threads for. I want the whole thing to be asynchronous, so I have throughputs, pipelines. Okay? So what I do, I use a for expression, and I use the future library. Okay? So I get person, and when the P comes out of the future into the reality now, I call friends of and send that off to go execute. I call interests of, send that off to go execute. And zip joins these together in the future and gives me back a tuple of friends and interests. When that comes back, then I create my front page context of the person, the friends, and the interests. Okay? This is the Scala futures. The Java futures actually can't do this. Java futures don't have a mechanism to continue on. after something is done. You usually have to block. And the key is the flat map method, but we can talk about that later. All right. So yes, this is the for expression where this happens. And see, I return a future front page context. So I can treat this new method as an asynchronous method. And I don't really care about all the things that are happening underneath. I just know eventually I'll get a front page, and I can define my pipeline. So now, this is basically what happens. When I call getPerson, it spawns off a future to getPerson. All right? I'm staging off something to do friends of. I'm staging off something to do interests of. I'm staging off something to zip those two things together, meaning when they're both done, I'm going to get a single value. And then I am returning the front page context. So I stage this computation. This is how things are going to flow. These are my listeners for when this is done, then this thing will execute. When this is done, this thing will execute. When getPerson returns the P, it notifies the other features. Hey, there's data. Friends of gets its thing, notifies. Interest gets its thing and notifies. Zip gets its thing and notifies. And then front page context gets its thing and is done. Okay? So it's all asynchronous. When one happens, it feeds off to the second one. The interesting thing here, in terms of FP patterns, zip has a funny name. It's kind of a bad name because it comes from math, so they just like to name things weird. But it's an applicative functor. Okay? But that's a pattern that is going to be very common, especially with asynchronous programming. The for expression, where you have something, 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 you've probably done this before. That's called a monad. It has to be a monad for that to work. And you are sequencing things. Okay? Those are the FP patterns that you can look into. They're not actually scary, just the names are. So, with that said, we did a big whirlwind tour of Scala and best practices and things to know, things to utilize, things that are good. We have 14 minutes left for Q&A. Yeah, any questions? I know that Daniel had one. Yes? What is the relation between a future and a stream? Good question. So you mean a Scala stream or just a stream in general? Okay, a Scala stream can actually have multiple values, and it's lazily evaluated, but it's not necessarily inside of like a thread pool. Okay, whereas a future can only have one value in it, and it may or may not be completed. So, you know, a future is a task that goes off onto a thread pool, and then when it's executed, when all of the information needed for it is ready, it executes, it gets its value, and it notifies anyone who needs it. Okay? So if you use map or flat map, that's when it notifies people that things are done. Versus a stream, I define a stream of some computation, where as I iterate over the stream, it's going to complete the computation, but it's going to do so on my thread. If that makes sense. Okay. Way up here. So the question is, do I have recommendations for resources or handouts on functional programming in Scala? Obviously, I'm going to recommend my book. There's a functional programming chapter at the end. There's also a book called Functional Programming in Scala by Paul Chisano and Runaroma, Bjarnson, I'm terrible with the name. That's also another good book. It has a lot of great examples. So those are the two that I'd recommend right now. If you want to learn, if you're interested in learning another language, Real World Haskell has a lot of good examples and applications of some of the stuff. And the Martin Odersky Coursera course is actually pretty awesome and free. So it depends on what kind of things you're trying to learn. Yes? So the question is, how can you combine monads and applicative functors in a for loop, which is
basically monad-based,
which is monadic-based? So if you look at what I did here, when I combined, can you read that code? That's really tiny.
it's a zip one, which is
I'm using zip inside of it. So the sequence is monadic, and to use applicative functors, you use that zip function right in line. Yeah, that's how I'm doing. Yeah, I'm hoping for a better.
the outer thing is still a monad, but internally used an
Yeah, the outer thing is a monadic workflow. Inside is that applicative functor to zip things together. Yes.
get those two in parallel.
Yes.
Okay,
Yeah. So those two calls go in parallel because of the zip. Yeah, not because of the for expression. Yes. Okay. Yeah, any other? I can't hear you. I'm sorry. Okay, so the question is, can I give example of the new Scala trait try in 2.10, because there's a lot of buzz. First, I'm going to talk about what try is actually meant for. So there's a class called try in Scala, where I can say try of some expression. Oh, yeah, I got to import it. I can say try of some expression, and it will try to run it. Okay? If there was no exception thrown, or no non-fatal exception thrown, I'll get a success object back. If there's an exception thrown, I'll get back a get back a failure method. Okay, where the failure method has the exception that was thrown. So this is a way that I can basically call a block of code and capture whether or not there was an exception thrown inside of a try. This is mostly meant for if I need to take an exception and pass it to another stack. So the problem with exceptions, and this is the problem that annoys the heck out of me, that I kind of like actors design for, is it's within a lexical scope, which means if there's a failure, the caller of the component that failed has to know how to recover. Where usually I want to do two things. I want to give the caller the error status so it can immediately do something useful, but I also need to recover the component that failed. All right, so what try is more about is I need to take that exception, capture it, and give it to somebody who can actually handle it. We use them in futures because in futures, I'm running something on some random thread. So when there's a failure, I need to basically say this job is done. Okay, I can kill that job, but I need to return the exception to the person who called me as well so they can do something useful because now they know the future's dead, if that makes sense. So it's about passing exceptions to other stacks, right? Other threads of execution. You can do a lot of neat things with try, with for expressions and that sort of thing. I'm not going to dig into it further. I recommend looking at it. It's nice. If you want to do, say, validation, like form validation, that sort of thing, try isn't going to be the best. It's not really designed for that. It's more designed to catch exceptions, lift them up, and pass them to a different stack. That's exactly what it's for. Any other questions? Yes?
So in one of your first slides, you had a for loop over people, and you did a toSet with a type parameter. I was wondering, can you provide further?
Okay, so the question is, in one of my earlier slides, I did a for expression with a toSet, and I had a type parameter in the toSet. And can't the compiler infer it? And the answer is no. It's one of the most frustrating bits of the compiler that we've tried to fix. That's actually a really, really, really hard type problem because of covariance, contravariance, set is invariant, and it's an explosion of things in the compiler where you should provide the type parameter. Trust me, if you try it on your own, just provide the type parameter when you call toSet, always. Okay, that's just easier. Good question though, yeah. Okay, Daniel.
So following up on that one real quick, it does actually work in a lot of circumstances, but you don't want it to. You don't want to try to exploit the functionality that makes toSets sometimes work without the type, because it just like the compiler goes mad. So your advice is like super, super, super good, and I should follow it more often. But my question actually, like back to where you had the traits, and you were encouraging people to use defs rather than vals, right? And then you mentioned area. You can take that from a def and turn it into a lazy val. The problem with that is that lazy val has an enormous amount of overhead associated with it. So the question is, do you have any like one-button general rules for when you should use lazy val, when you should like consider moving things around? Is there a good pattern to watch out for when lazy val might be a problem? What's your advice?
Yeah, so the question is specifically about lazy val. So when we were talking about object orientation and the initializing problem that you have when you have traits and multiple traits being added, and you define a lazy vals actually have an overhead associated with them. So lazy vals, you end up getting a synchronization block around them. So anytime you access it, you hit synchronization. So that is an issue. Do I have any suggestion of when to use them? Essentially, if if you're running, I don't have any real good rules of thumb. Besides, if you have performance-intensive code, I would actually tend to avoid lazy values unless it's the best solution. Lazy value is the best solution for computing something once and only once and storing it. I actually tend to prefer methods rather than lazy val for that exact reason. If it's something nice and small, the method is going to be better. If performance of lazy vals becomes a problem, that's when you move to early initializers. But again, I would tune your application always and understand where your performance bottlenecks are. If it's the lazy value, then it's the lazy value, and then you can look at fixing it. Premature optimization is obviously the root of all evil. From what we've seen, there's a portion of our app where we have to avoid using lazy vals, but it's a lot smaller than you would expect based on the overhead of lazy val, if that helps.
Is it not somewhat unavoidable if you have mutual recursive initialization?
So the question is it not unavoidable to use lazy val if you have mutually recursive invocations? And yes, you have to use lazy val in that case, yeah, because you're trying to make something immutable, and you can only instantiate it once, and if it mutually is recursive, lazy val can actually solve that problem.
Well, back to me. So if you have a mutual recursive evaluation, right, there has to be some linearization, otherwise it's back to me. So either it's going to be completely recursive forever, or there's going to be a linearization to it. You can always linearize that by hand. So lazy val isn't unavoidable, you just have to do a double initialization with a bar to get around it.
Good answer, man. You want to come anyway? Yeah, there was another question. Yes.
Can you provide the hash codes for case classes, or is it just always automatic?
So the question is, can you provide a hash code for case classes, or is it automatic? If you write a method for a case class, the compiler will not write it for you. So if you provide your own, that's fine. That'll work fine. We won't provide one. But if you don't provide one, we provide it. It's the same with equals. The method you want to watch out for is you don't really want to provide unapply, and you don't really want to provide apply in the companion object. Those are the two you should not do, because you're basically asking for pattern matching to explode. But yeah, anyway, you can totally do that. Yes?
How big is a case class overhead compared to a simple POJO?
So the question is, how big is case class overhead compared to a regular POJO? So case classes add the serialization interface. Okay, they add a 5 or 6 methods on the class itself. So I would say the overhead is minimal compared to a full-up POJO. You get a getter. You don't get setters. You get a copy method instead of the setters, so you have one less method there. And then you have a bunch of default parameter methods. So on average, we have maybe like 5 to 10% more bytecode for the class itself. Now, there's also a companion object that lets you do the deconstruction, that lets you do the pattern matching. And so that obviously is a bit more. But the class itself, there's not a lot of overhead, and it takes up the same amount of space in the memory, right? So there's no like object allocation overhead on the heap or anything. Just bytecode. Yes.
At Tickle's session yesterday, there was asked a question about case classes, and they can't inherit from another case class.
Yeah.
I see some examples even in this year's book where they have this kind of enumeration hierarchy of case classes. So is the only way to solve that to use multi-classes?
So the question is, about case classes inheriting from other case classes. The answer is no, we don't let you inherit from other case classes. If you have a chance to buy my book, or buy actually the Programming Scala book by Bill Venners, you'll see that inheritance really kills equality. If you want to provide a default equality method in the presence of inheritance, it's really impossible for the compiler to do the right thing. So case classes are the leaf nodes. We can define equality if we are at the bottom, but we can't if we're in the middle of inheritance, because we don't know if this case class and its sub-case class can be equal or not. We don't know if that's a valid relationship between the parent-child. For that reason, we've locked case classes. They can only be the leaf nodes. If you do get Scala In Depth, it's in chapter 2 about equality and how to compose equality for inheritance, which is actually quite difficult. It's far easier if you use immutability, and usually you don't need equality on, say, your business classes that use inheritance, but your data layer usually has leaf nodes. You know, like this is a person, this is a computer, you know, this is a product I'm selling. So usually those are just fine using case classes, and that's what they're designed for. Yeah. I have 1 minute left, so it better be a 1 minute question, Daniel.
It'll be very quick.
Okay.
Is the case classes locked for inheritance? Is that something that's new in 210?
The case class is being locked for inheritance. Is that something new in 210? I believe that it is new-ish. I don't remember if it was 2.9 or 2.10. My brain is fuzzy between the two since I've been doing 2.10 for so long. But if it's not in 2.9, it's definitely enforced in 2.10. Yeah, and that's it. Thanks, guys.